NENOMATICA, where mathematics meets YouTube excellence. Exponential equations. Welcome to our lesson on exponential equations. Today, we'll learn how to solve equations where variables appear in exponents. These are called exponential equations, and they require special techniques to solve. Let's dive into some examples. Let's look at our first example. We have 8 times 2 raised to the power of 2x squared plus 2 equals 2050. Let's solve this step by step to find the value of x. Let's start solving this equation. First, we'll isolate the term with the variable. We subtract 2 from both sides of the equation, giving us 8 times 2 raised to the power of 2x squared equals 2050 minus 2. Next, we simplify the right side and get 8 times 2 raised to the power of 2x squared equals 2048. Now, let's rewrite the left side. We can express 8 as 2 to the power of 3, giving us 2 to the power of 3 times 2 to the power of 2x squared. Using the law of exponents, we can combine these terms with the same base. When multiplying powers with the same base, we add the exponents. So we get 2 raised to the power of 2x squared plus 3 equals 2048. We know that 2048 can be written as 2 to the power of 11. So our equation becomes 2 to the power of 2x squared plus 3 equals 2 to the power of 11. When two powers with the same base are equal, their exponents must be equal. This is a fundamental property of exponential equations. So we can write 2x squared plus 3 equals 11. Now we can solve for x squared. First, subtract 3 from both sides. We get 2x squared equals 8. Dividing both sides by 2, we get x squared equals 4. Taking the square root of both sides, we get x equals plus or minus 2. So the solutions for this equation are I2. We get x squared equals 4. Taking the square root of both sides, we get x equals plus or minus 2. So the solutions for this equation are x equals 2 or x equals negative 2. Let's move on to our second example. In this example, we have the fraction 1/3 raised to the power of 2 minus x equals 243. First, let's rewrite this using a negative exponent. The fraction 1/3 can be written as 3 to the power of negative 1. So we have 3 to the power of negative 1, and that entire expression is raised to the power of 2 minus x. Using the law of exponents, when we raise a power to another power, we multiply the exponents. So we get 3 raised to the power of negative 1 times 2 minus x, which simplifies to 3 raised to the power of x minus 2. Simplifying the exponent, we get 3 to the power of negative 2 plus x, which can be written as 3 to the power of x minus 2. We know that 243 equals 3 to the power of 5. So our equation becomes 3 to the power of x minus 2 equals 3 to the power of 5. Again, when two powers with the same base are equal, their exponents must be equal. 3 to the power of 5. Again, when two powers with the same base are equal, their exponents must be equal. So, we need to solve the equation left parenthesis 1 over 25 right parenthesis raised to the power of 2x times 5 raised to the power of x minus 2 equals 5. To solve this equation, we need to simplify by converting all terms to the same base. First, we'll rewrite 1 over 25 as 5 raised to the power of negative 2. So our equation becomes open parenthesis 25 raised to the power of negative 1 closed parenthesis raised to the power of 2x times 5 raised to the power of x minus 2 equals 5. Next, we can rewrite 25 as 5 squared. So our equation becomes open parenthesis 5 squared closed parenthesis raised to the power of negative 1 closed parenthesis raised to the power of 2x times 5 raised to the power of x minus 2 equals 5. Now, we'll apply the exponent rule that states when a power is raised to another power, we multiply the exponents. This gives us 5 raised to the power of negative 2 times 2x times 5 raised to the power of x minus 2 equals 5. Now, we can simplify the first exponent by multiplying. This gives us 5 raised to the power of negative 4x times 5 raised to the power of x minus 2 equals 5. Using another exponent rule, when multiplying powers with the same base, we add the exponents. This gives us 5 raised to the power of negative 4x plus x minus 2 equals 5. Let's simplify the exponent by combining like terms. Negative 4x plus x gives us negative 3x, And then minus 2 gives us negative 3x minus 2. So we have 5 raised to the power of negative 3x minus 2 equals 5. When we have the same base on both sides of the equation, the exponents must be equal. So negative 3x minus 2 equals 1. Now let's solve for x. First, we add 2 to both sides, which gives us negative 3x equals 3. Finally, we divide both sides by negative 3. This gives us x equals negative 1, which is our solution. Now, let's move on to our second example. Here we need to solve 2 raised to the power of 2x minus 1 plus 1 equals 9. Let's start by isolating the exponential term on the left-hand side. We subtract 1 from both sides, which gives us 2 raised to the power of 2x minus 1 equals 8. Next, we simplify the right side. 9 minus 1 is 8. Now we'll rewrite 8 as 2 cubed, since having the same base on both sides will help us solve the equation. So we have 2 raised to the power of 2x minus 1 equals 2 raised to the power of 3. Since the bases are the same, the exponents must be equal. So 2x minus 1 equals 3. To isolate the term with the variable, we add 1 to both sides. This gives us 2x equals 4. We can rewrite 4 as 2 squared. So we have 2 raised to the power of x equals 2 raised to the power of 2. Once again, since the bases are the same, the exponents must be equal. So x equals 2, which is our solution. We need to solve the following exponential equation. The fraction 1 over 49 raised to the power of x minus 3 halves multiplied by 7 to the power of x equals 7 to the 4th power. First, let's rewrite the fraction 1 over 49 as 49 to the power of negative 1. This makes it easier to work with the exponents. Next, we can rewrite 49 as 7 squared. Now, we'll use the power to a power rule. When we raise a power to another power, we multiply the exponents. So 7 to the power of negative 2 raised to the power of x minus 3 halves becomes 7 to the power of negative 2 times x minus 3 halves. When multiplying expressions with the same base, we add the exponents. So 7 to the power of negative 2x plus 3 multiplied by 7 to the power of x equals 7 to the power of negative 2x plus 3 plus x. Let's simplify the exponent. Negative 2x plus 3 plus x equals negative x plus 3. When we have the same base raised to different powers that are equal to each other, we can set the exponents equal to each other. So negative x plus 3 equals 4. Subtracting 3 from both sides, we get negative x equals 1. Finally, multiplying both sides by negative 1, we get x equals negative 1. This is our solution. Now, let's move on to our second example. Here's our second example. 8 to the power of x plus 2 equals 8 times 3 to the power of 4x plus 4. First, let's rewrite the right side by factoring out the constant. We can rewrite 8 times 3 to the power of 4x plus 4 as 8 times 3 to the power of 4 times x plus 1. Now, let's manipulate the left side of the equation. We'll rewrite 8 to the power of x plus 2 as the fraction 8 to the power of x times 8 to the power of 2 over 8 to the power of 0, which is just 8 to the power of x times 8 squared divided by 8. Simplifying, we get 8 to the power of x times 8 to the power of 1 equals 81 to the power of x plus 1. Combining like terms, we get 8 to the power of x plus 1 equals 81 to the power of x plus 1. In this last equation, we have the same exponents but different bases. For this equation to be true, either the exponents must be 0 or the bases must be equal. Since the bases 8 and 81 are not equal, the only way this equation can be true is if the exponent x plus 1 equals 0. Let's verify our solution by substituting x equals negative 1 back into the original equation. Let's review some important rules of exponents that we used in these examples. In summary, we've learned how to solve exponential equations by 1. Using the properties of exponents to simplify expressions. 2. Getting the same base on both sides when possible. 3. Setting exponents equal when the bases are the same. 4. Finding alternative solutions. When bases differ, remember to verify your solutions by substituting back into the original equation. In our next lesson, we'll explore more complex exponential equations, including logarithms. 3 to the power of x plus 3 to the power of x plus 1 plus 3 to the power of x plus 2 plus 3 to the power of x plus 3 equals 360. First, we'll rewrite each term to highlight the pattern. Notice that 3 to the power of x plus 1 can be written as 3 to the power of x multiplied by 3 to the power of 1. Similarly, 3 to the power of x plus 2 equals 3 to the power of x multiplied by 3 squared. And 3 to the power of x plus 3 equals 3 to the power of x multiplied by 3 cubed. Now, we can factor out 3 to the power of x from all terms. This gives us 3 to the power of x multiplied by the sum, 1 plus 3 plus 9 plus 27. Adding these values, we get 3 to the power of x multiplied by 40 equals 360. Dividing both sides by 40, we get 3 to the power of x equals 360 divided by 40. Simplifying, 3 to the power of x equals 9. Since 3 to the power of x equals 9, and 9 equals 3 squared, we can write 3 to the power of x equals 3 squared. When bases are the same, the exponents must be equal. So x equals 2. Remember this important rule when working with exponential equations. When the bases are the same, the exponents must be equal. This allows us to write, if a to the power of m equals a to the power of n, then m must equal n. Now let's move on to our second example. 5 to the power of 2x plus 1 plus 25 to the power of x minus 5 to the power of 2x plus 2 plus 25 to the power of x plus 1 minus 5 to the power of 2x equals 5 to the power of 101. First, let's rewrite some terms. 5 to the power of 2x plus 1 can be written as 5 to the power of 2x multiplied by 5 to the power of 1. 25 to the power of x is already in a good form, as 25 equals 5 squared. 5 to the power of 2x plus 2 can be written as 5 to the power of 2x multiplied by 5 squared. And 25 to the power of x plus 1 can be written as 5 to the power of 2 times x plus 1. Let's simplify further. We have 5 to the power of 2x times 5 plus 5 to the power of 2x minus 5 to the power of 2x times 5 squared plus 5 to the power of 2x times 5 squared minus 5 to the power of 2x equals 5 to the power of 101. We can factor out 5 to the power of 2x and simplify inside the parentheses. We get 5 to the power of 2x multiplied by the sum. 5 plus 1 minus 25 plus 25 minus 1. Simplifying inside the parentheses, we get 5 to the power of 2x times 5 equals 5 to the power of 101. We can rewrite this as 5 to the power of 2x plus 1 equals 5 to the power of 101. When bases are the same, the exponents must be equal. So 2x plus 1 equals 101. Solving for x, we first subtract 1 from both sides, getting 2x equals 100. Finally, dividing by 2, we get x equals 50. Here are some important rules to remember when working with exponential expressions. First, when multiplying terms with the same base, add the exponents. Second, remember that a to the power of m equals a to the power of n implies m equals n. Third, when raising a power to another power, multiply the exponents. And an important warning, a to the power of m plus a to the power of n is not equal to a to the power of m plus n. This is a common mistake to avoid. We have a complex exponential equation that we need to solve for x. First, let's simplify the expression by applying exponent properties. In the numerator, we have 3 to the power of 2x plus 3 to the power of 2x minus 1. We can rewrite the second term as 3 to the power of 2x multiplied by 3 to the power of negative 1. Now we know that 3 to the power of negative 1 is equal to 1 over 3, so we can write this as 3 to the power of 2x plus 1/3 times 3 to the power of 2x. Next, we can factor out 3 to the power of 2x from the numerator. This gives us 1 plus 1/3 times 3 to the power of 2x. Let's now look at the denominator. We have 2 times 8 to the power of x plus 8 times 2 to the power of 3x. First, let's recall that 2 to the power of 3x is the same as 8 to the power of x because 8 equals 2 cubed. So our denominator becomes 2 times 8 to the power of x plus 8 times 8 to the power of x, which can be factored as 2 plus 8 times 8 to the power of x, or 10 times 8 to the power of x. Meanwhile, in the numerator, 1 plus 1/3 simplifies to 4/3. So we now have 4/3 times 3 to the power of 2x over 10 times 8 to the power of x. Now, let's simplify further. We have 4/3 times 3 to the power of 2x over 10 times 8 to the power of x equals 3 over 20. We can note that 3 to the power of 2x is equal to 9 to the power of x because 3 squared is 9. So we have 4/3 times 9 to the power of x over 10 times 8 to the power of x equals 3 over 20. We can rearrange this to get 4 over 30 times 9 over 8 to the power of x equals 3 over 20. Multiplying both sides by 30 over 4, we get 9 over 8 to the power of x equals 30 times 3 over 20 times 4, which simplifies to 9 over 8 to the power of x equals 30 times 3 divided by 20 times 4. Simplifying the right side, we get 30 times 3 is 90 and 20 times 4 is 80. So 90 over 80, which further simplifies to 9 over 8. So we have 9 over 8 to the power of x equals 9 over 8. Since the bases are the same on both sides, the exponents must be equal. So x equals 1. Now, let's solve another example. For our second example, we need to solve a more complex exponential equation. First, let's rewrite the term with the exponent 2x minus 1. We can express this as 9 over 64 to the power of 2x times 9 over 64 to the power of negative 1. Now, we can rewrite 9 over 64 to the power of negative 1 as 64 over 9. Let's rewrite this to expand out the exponents more clearly. We have 3 to the power of x times 8 to the power of x times 8 over 3 to the power of x times 9 squared x over 64 squared, x times 64 over 9. We can simplify this by canceling the 3 to the power of x in the numerator with the same term in the denominator of the second fraction. Now our equation becomes 8 to the power of x times 9 to the power of 2x divided by 64 to the power of 2x times 64 over 9 equals 9 over 8. Now, let's note that 64 is 8 squared. So 64 to the power of 2x is equal to 8 to the power of 4x. Our equation becomes 8 to the power of x times 9 to the power of 2x divided by 8 to the power of 4x times 64 over 9 equals 9 over 8. Simplifying the 8 terms, we get 8 to the power of x divided by 8 to the power of 4x, which is 8 to the power of x minus 4x, or 8 to the power of negative 3x. So our equation becomes 8 to the power of negative 3x times 9 to the power of 2x times 64 over 9 equals 9 over 8. Let's continue to simplify. 8 to the power of negative 3x is 1 over 8 to the power of 3x. Also, 64 is 8 squared. So we have 1 over 8 to the power of 3x times 9 to the power of 2x times 8 squared over 9 equals 9 over 8. Moving all the terms to one side, we get 9 to the power of 2x times 8 squared over 8 to the power of 3x times 9 equals 9 over 8. Let's simplify this expression. We have 9 to the power of 2x over 9 times 8 squared over 8 to the power of 3x equals 9 over 8. We can simplify the 9 terms to get 9 to the power of 2x minus 1. Similarly, for the 8 terms, we have 8 to the power of 2 minus 3x, which is 8 to the power of 2 minus 3x. So our equation becomes 9 to the power of 2x minus 1 times 8 to the power of 2 minus 3x equals 9 over 8. For an exponential equation to be true, both sides must represent the same value. If we look at what we have, 9 to the power of 2x minus 1 times 8 to the power of 2 minus 3x equals 9 over 8. We can rewrite the right side as 9 times 1 over 8. Then we have 9 to the power of 2x minus 1 times 8 to the power of 2 minus 3x equals 9 to the power of 1 times 8 to the power of negative 1. Since the bases are the same on both sides, the exponents must be equal. This gives us 2x minus 1 equals 1, and 2 minus 3x equals negative 1. From the first equation, we get 2x equals 2, so x equals 1. Let's verify this with the second equation. 2 minus 3 times 1 equals 2 minus 3, which is negative 1. This confirms that x equals 1 is our solution. Let's highlight an important rule we used in solving these problems. When solving exponential equations, a key strategy is to rewrite all terms using the same base. This allows us to compare the exponents directly. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.